Okay, so as we just said, there are lots of trees, potentially an infinite space if we consider branch length. So when one is given a certain number of taxa to infer phylogeny, researchers, phylogeneticists have devised many different types of algorithms to infer the most probably correct tree. So these methods can be classified into 4 families. The first family is the family of distance matrix methods. Their goal is to infer a tree from an input being a matrix of pairwise distances between the different taxa. Okay, so if you have n taxa, you would have an n times n matrix of distances, and most usually your distances are symmetric, so you can have only half this matrix. And from these distances between taxa, you're going to try and design the best tree. So we're going to see these some of these methods today. Another class of methods to reconstruct a phylogenetic tree is the minimum evolution kind of techniques, and minimum evolution is the same as maximum parsimony. Okay, the idea in these 2 methods is to say, okay, the best tree is probably the one that leads to the minimum amount of substitutions, of mutations, if you want, on the branches. Okay, so it comes with this strong assumption that the best way to model reality is to explain evolution with the minimum amount of evolutionary events. A third family of methods is the maximum likelihood methods. For these methods, the best tree is the one that maximizes the probability of the data observed on the leaves under a certain evolutionary model. So we talked about this in the question and answer session yesterday, and we're going to define likelihood again in our last session on the first of on day 4. The likelihood is the probability of the data knowing the model, and maximum likelihood methods try and maximize this certain probability. Bayesian methods try and associate trees with posterior probabilities, the posterior probability of a model, and they try to pick the model that has maximum posterior probability. So it's a different viewpoint than maximum likelihood, and practically it's a viewpoint that leads to more complex calculations and that is more computationally demanding, in fact. So let's start with the family of methods based on a distance matrix. This is the most ancient, or the oldest family of methods to build phylogenies, and the underlying ideas are straightforward, and what is very convenient is that these methods, these techniques, enable one to build phylogenies based on many different traits, be they quantitative or qualitative. And that's why these techniques are very appealing, and still nowadays they are very widely used. So the advantage, as I just said, is that they can be used on virtually any data, as long as one knows how to calculate pairwise distances from your traits, whatever your traits, then you are good to go and use a distance matrix method. For instance, if you build a phylogeny on a quantitative trait, then that's extremely simple to devise a distance between taxa, because basically if you say I'm building a phylogeny of mammals based on the diameter of the skull is measured in millimeters, for instance, and so it's a basic number, a real number. So the distance between two real numbers is very straightforward. Okay, so you can build phylogenies on quantitative traits more easily maybe than with maximum likelihood methods, because maximum likelihood methods ask you to define a model of evolution. Okay, here for distance matrix methods, you don't need a model of evolution. You just need to know how to calculate distances between any given two taxa, right? So another advantage is that distance matrix methods are fast. They accommodate even large numbers of taxa because of their speed. Okay. The shortcoming is that most often the calculated distances differ from patristic distances. We're going to see this again later, but basically in your matrix, let's imagine you have two taxa that were taxon 1 and taxon 10. Okay. In your matrix, you have a certain distance. In your input matrix, you have a certain distance between taxon 1 and taxon 10, right? Let's say this distance was 10, and then you build your tree with an automatic method of distance based tree reconstruction. And finally, what you find if you sum the length of all the branches on the path between taxon 1 and taxon 10 in your tree, this sum of length is different from your original value for the distance between taxon 1 and taxon 10 that you had in your matrix. Okay, and it's quite inevitable. So that's a shortcoming. You start with a certain number of distances that are in your matrix, and you get a tree. But ultimately, when you measure actually the distances between taxa as what we call patristic distance, as the sum of the branch length on the path linking the said taxa, then you don't get the same value as what you had initially in your matrix. So it's inevitable. It's because the constraint of the topological constraints of having a tree make it that you cannot, let's say, satisfy all the constraints that are in your initial matrix in terms of pairwise distances. There is a loss of signal from the data also, because in any case with distance matrix methods, the first step is to move away from the original data to a distance matrix, and after that, when you build your tree based on this distance matrix, the original complexity of the data is not completely forgotten, but any taxon is reduced to the expression of its distances with the other taxa, and that's all. Okay. So the complexity of the data of a taxon is summarized into its pairwise distances with others. Some methods produce constraint trees. We're going to see later what's this constraint of molecular clock. So we're going to see in detail the simplest distance matrix methods. Its name is not the simplest, but the technique is quite simple, as you will see. So it has been designed by Sokal and Michener in 1958, and UPGMA stands for Unweighted Pair Group Method using arithmetic averages. How does it work? it builds the tree kind of from the leaves to the root. Okay, it builds gradually the tree, aggregating leaves together. So aggregating or grouping taxa into clusters, and it builds the tree bottom up from the trees to the root. The distance between two clusters is the average distance between pairs of sequences from each cluster. Okay, you're going to build these clusters gradually according to this, and you're going to determine the branch length of the new branches that you build according to this rule. Distance between two clusters is the average distance between pairs of sequences, one in one cluster and in the other cluster. Okay, that's the rule to calculate the branch length that you're going to for the branches that you're going to add progressively to your tree being built. And it's a greedy algorithm. Okay, greedy algorithm meaning that you never undo what you've done. So you never go back in the process of building your tree. You make decisions about, okay, I'm going to select this cluster and this other cluster and link them with a branch, and you will never undo this new cluster that you formed from two previous clusters. So the description of the algorithm follows in these 3 bullet points. Initially, you have as many clusters as individual sequences. So one sequence, one taxon makes one cluster. Okay, so we are at the bottom of the tree. For at the moment, there is no tree yet. There are only single leaves. So they are at the bottom. We say they are at height 0. Iteratively choose the two clusters C1, Ci, and Cj. So let's forget about this for 1 second. The rule is that you're going to say, okay, at any given time when I need to add a new branch, I'm going to try and see what are the taxa, the two closest taxa. Okay? At the beginning, we start with taxa. So you're going to say, what are the two closest taxa, meaning what is the minimum distance in my current matrix of distances. What is the minimum distance? You find that it's the distance between taxon A and taxon C. Then you will say, okay, I group these two and I build a branch from taxon A to taxon C, and I calculate the distance, the length of this branch will be the length of, or the distance seen in the matrix. And then you have n-1 cluster. We start with n clusters, okay? But after grouping together the closest leaves, you have n-1 clusters, right? Because you grouped two leaves into one cluster, okay? So we started with leaves, but gradually you form clusters. So now after the first grouping, we have, if we had originally n taxa, we have one cluster that is made of the two closest taxa, and we have n-2 clusters, the other clusters, that are made of the individual taxa left, that have not been grouped yet. So iteratively, you will continue at each step of this, at each iteration, you choose the two clusters that have the minimum distance, and you define a new cluster that contains all the sequences from these two clusters, and you place the corresponding node at the height d from I to j divided by 2, and link it with the two nodes representing Ci and Cj. It's very abstract here. We're going to see how it works, and you will no longer be lost. And you continue this process until the root is reached, when all clusters are connected. So yeah, don't worry. You see it's going to be very simple in the next slide. But it shows you the beauty of these simple methods, distance matrix method, is that it's very easily explainable in just a few rules. We're going to see how it works, okay? So let's start with this example. I imagine I have 4 taxa. When I have 4 taxa, my distance matrix looks like this. As we said earlier, we most often have symmetric distances, okay? And in fact, in mathematical terms, a true distance must be symmetric. a true metric must be symmetric, so it means that the distance between A and B must be the same as the distance between B and A. Okay, the distance from A to B is the same as the distance from B to A. So here I could have written a 9 here because it's B to A, or here A to B. But just to make it lighter, this matrix is non-redundant, so every information is present only once. And so I don't have 9, 7, 3, 5, 6, 2 in these. I just write the upper right half matrix. And obviously here the distances are 0. There is distance 0 between A and A, or between B and B, etc. So we just don't represent them. Okay, so I have my full distance matrix here. First step is to see, okay, which are the two taxa that appear to be closest to each other. Which are the two taxa that have smallest distance. So here, and if they were ties, we just choose one pair amongst those who tie. Choose one pair at random. Here we do not have any tie. We see that it's B and C that are closest. So I know I will link them into one cluster. Remember that we are building a tree from bottom to top, and so all taxa at the beginning are at ground level, at level 0 if you want. Okay, level 0 is the current time. Okay, if you make an analogy between distances and evolutionary time. So now remember, when we calculated the evolutionary distances, it's obvious that in this tree, the distance between B and C, what we call the patristic distance between B and C, is the sum of the length of the branches in the unique path from B to C, or from C to B, and this sum is here 1 plus 1, and it's 2. Okay, so we build a new cluster BC, and the node that connects these two these two leaves is a node placed at a height that is equal to the distance between B and C divided by 2. Right? So it's 1 here. Now that we have a new cluster BC, we will have to produce a new distance matrix, because now we no longer consider B and C as individual taxa. We consider one cluster whose virtual position is here. That's the node here. And we consider this one cluster, and this one cluster, we must calculate its distance to any other taxa. Okay? So we have B and C. How do we calculate the distance between this cluster and A, and the distance between this cluster and D? We, as I said earlier, the distance between two clusters is the average distance between pairs of sequences from each cluster. So here, the distance between the new cluster BC and A is equal to the average of the distance between B and A and between C and A, right? So we have B to and A distance 9, C and A distance 7. So the new distance between the cluster BC and the cluster A is 8. 9 plus 7 divided by 2, right? Similarly, for the distance between the cluster BC and the cluster D, we have distance from B to D plus distance from C to D divided by 2. Okay, B to D 6, C to D 5 divided by 2, 5.5. Okay, so now in the next slide you're going to see a modified distance matrix that we're going to work with, and this modified distance matrix that you'll see in the next slide is a matrix 3 by 3. Okay, and you have A, B, C, and D. And here similarly A, B, C, and D. And this new matrix is now formed of these new values that we calculated and the former distances. Okay, nothing changes concerning, for instance, the distance between A and D. Not for instance, it's the only one that remains. A and D was a distance 3. A was a distance 3 to D and from D, and we'll keep that. Okay. So this 3 remains, A to D is there, and we have our new distances, A to BC 8 and BC to D 5.5. Okay? That's what I wrote here. 8 and 5.5. Right. Now you work with this new matrix, and iteratively you do the same as what we've done earlier. Find what is the smallest number in this matrix. The smallest number is here. It links A to D. So we are going to define a new cluster A to D. The previous cluster still exists. I've not represented it on this slide, but you have BC here, okay, with distance 1, distance 1. I've not represented it here. Now A and D, A is at distance 3 to D, so you try and do your best to respect this, and in fact it's always possible when you have just two taxa, to respect the patristic distance. So from A to D you have distance 3, so this node is at height 1.5, okay? New cluster AD. And now we have the new cluster AD and the cluster BC. We have to calculate the distance between AD and BC. Distance between BC and AD, that's the distance between BC. Now we have calculated BC is one cluster, so we take the mean of the distance between BC and A and the distance between BC and D. Okay? So it's 8 and 5 plus 5 divided by 2, it's 675, right? So we would have another matrix, a distance matrix, but that contains just one value now, and linking BC and AD is 6.75. So that's what we have. Finally, we had our cluster BC, okay? Distance 1 for the branches linking B or C to their common ancestor, most recent common ancestor. We have our cluster AD, and we just have calculated, so with 1.5, 1.5, and what we calculated is that the distance between BC and AD is 6.75. It means that the node that links the clusters BC and AD will be at height 6.75 divided by 2. So the distance of BC to AD is 6.75. It's not correct to say this is this height. This height is this divided by 2, right? So this height is 3.375. Okay, and that's indeed 2.375 plus 1. Okay, 3.375 times 2 is 6.75, right? And then so you calculate the branch length here, that is this divided by 2 minus 1.5 to get this distance, right? So you have your final tree, and this tree is rooted. So UPGMA technique gives you rooted trees. Let's have a break.